Okay, my dear students, already you learned about Gauss theorem. According to Gauss theorem, the total electric flux across any closed surface in air medium is always equal to 1 upon epsilon naught times of total charge enclosed by that surface. This is Gauss theorem. In this video, we are going to study what are the applications of Gauss theorem. What is the use of Gauss theorem? My dear students, consider a charge Q. This is a point charge. It is having electric field around it. Now, let us consider a point P at a distance R from the point charge Q. Then electric intensity at a point P acts in this direction since it is a positive charge. Now, the magnitude of this intensity at point P due to this point charge is given by E equal to K into Q upon R square. Getting the idea? This is the intensity at a point P due to a point charge. But now my question is, consider a sphere. This is a sphere of radius R. Getting the idea? Now, I will charge this sphere like this. These are the charges found on the surface of the sphere. Since this sphere is charged, it is having electric field around it. Now I will consider a point P at a distance R from the center O of the sphere. Since the point P is present in an electric field of this charged sphere, here intensity will happen. Now what is the intensity at a point P due to this charged sphere? Here we can't use this concept because this concept is used, this formula is used for single point charge. But many charges are going to distribute on the surface of this sphere. In such cases, such type of distribution of charge is known as complex charge distribution. In such cases, we can't use directly this formula. In such cases, we will find the intensity at a point P by using Gauss theorem. Getting the idea? This is one of the applications of Gauss theorem. Now, I will consider one more example. Consider a wire here. When this wire is charged, here wire is positively charged. Since the wire is charged, it is having electric field around it. Now I will consider a point P at a distance R from the axis of the wire. Now what is the intensity at a point P due to this charged wire? Here also many charges are present throughout the length of the wire. Then what is the intensity at point P due to this charged wire? This can be calculated by using Gauss theorem. Here I will consider one more example. This is a plane sheet. This is also charged positively. Getting the idea? Here plane sheet is charged positively. That means it is also having electric field at the front and back side. Now I will consider a point P at a distance R from the plane sheet. Now what is the intensity at a point P due to this charged plane sheet? This can also be calculated by using Gauss theorem. Getting the idea? In this way, in this class we are going to study, in case of complex distribution of charges, how the intensity is calculated by using Gauss theorem. That we are going to study one by one. Getting the idea? Okay, let us start. Okay, my dear students, here I am going to derive the expression for electric intensity at a point due to a charged sphere using Gauss theorem. Here I have considered a sphere of radius capital R with center O. Now I will give Q amount of charge to this sphere. Then this Q amount of charge distributes uniformly over the outer surface of the sphere. Okay. Now the sphere is charged. This is called charged sphere. Since the sphere is charged, it is having electric field around it. Now what I am going to do, I am going to find electric intensity at a point outside the sphere or inside the sphere using Gauss theorem. Get the idea? ಇಲ್ಲಿ ನೋಡಿ ನಾವು ಒಂದು ಸ್ಪಿಯರ್ ಅನ್ನು ಕನ್ಸಿಡರ್ ಮಾಡ್ಕೊಂಡೀನಿ. ಅದರ ರೇಡಿಯಸ್ ಕ್ಯಾಪಿಟಲ್ ಆರ್, ಸೆಂಟರ್ ಓ ಇದೆ. ಇದನ್ನು ಚಾರ್ಜ್ ಮಾಡಲಾಗಿದೆ. ಎಷ್ಟು ಚಾರ್ಜ್ ಅನ್ನು ಕೊಟ್ಟಿದ್ದೇವೆ? ಕ್ಯೂ ಅಮೌಂಟ್ ಆಫ್ ಚಾರ್ಜ್ ಅನ್ನು ಕೊಟ್ಟಿದ್ದೇವೆ. ಓಕೆ, ಈ ಕ್ಯೂ ಅಮೌಂಟ್ ಆಫ್ ಚಾರ್ಜ್ ಯೂನಿಫಾರ್ಮ್ ಆಗಿ ಔಟರ್ ಸರ್ಫೇಸ್ ಮೇಲೆ ಡಿಸ್ಟ್ರಿಬ್ಯೂಟ್ ಆಗಿದೆ. ಈಗ ಗಾಸ್ ಥಿಯರಮ್ ಅನ್ನು ಬಳಸಿ ನಾವು ಏನು ಮಾಡಬೇಕು, ಒಂದು ಪಾಯಿಂಟನ್ನು, ಆ ಪಾಯಿಂಟ್ ಈ ಸ್ಪಿಯರ್ದ ಹೊರಗಿರ್ಬೋದು ಅಥವಾ ಒಳಗಿರ್ಬೋದು, ಆ ಪಾಯಿಂಟಲ್ಲಿ ಎಷ್ಟು ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಇದೆ, ಎಲೆಕ್ಟ್ರಿಕ್ ಇಂಟೆನ್ಸಿಟಿಯನ್ನು ಈ ಚಾರ್ಜ್ ಸ್ಪಿಯರ್ ಉಂಟು ಮಾಡ್ತಾ ಇದೆ ಅನ್ನೋದನ್ನು ನಾವು ಗಾಸ್ ಥಿಯರಮ್ ಬಳಸಿ ಕಂಡುಹಿಡಿಬೇಕು. ಓಕೆ, now I will consider a point P outside the sphere. Here I will consider a point P outside the sphere at a distance small letter r. At a distance small letter r. Okay, that means you can derive this expression in two cases. That is, first one is by considering the point P outside the sphere. First one case is point outside the sphere. Point outside the sphere. Getting the idea? Let P be a point outside the sphere at a distance r from the center O of the charge sphere. My dear students, if you want to find electric intensity at a point P, you have to imagine a sphere, a closed surface. You have to imagine a sphere or closed surface. Why you should imagine a closed surface, a closed sphere? Because you can apply the Gauss theorem only to closed surfaces. That's why I have considered a closed surface of radius small letter r. And my dear students, if you want to apply Gauss theorem, two conditions must be satisfied. What are those? At all points on the surface, the electric intensity should be same and it should act along the normal to the surface. If these two conditions are satisfied, then only we can apply Gauss theorem. And the surfaces which obey these two conditions are known as Gaussian surfaces. Now let us study this imaginary sphere obeys those two conditions or not. See here, I will consider point P here. Here I will consider one more point here, 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 here. At all these points, electric intensity is same. Why electric intensity is same? Because all these points are at equal distance r from the center O of the sphere. That's why electric intensity is same at all points on this imaginary sphere. That is, first condition is satisfied. And also you must remember here the sphere is charged positively. That's why intensity at point P due to this charged sphere acts radially outward direction. And here also radially outward direction. And here also radially outward direction. And here also radially outward direction. Getting the idea? That means here second condition is also satisfied. That is, electric field or electric field lines are acting normally to the surface. Here this electric field line is normal to this surface. This is normal to this surface. This field line is normal to this surface. This is also normal to this surface. All electric field lines are normal to the surface of the sphere. In this way, two conditions are satisfied here. That's why this imaginary sphere is considered as Gaussian sphere. Getting the idea? ನೋಡಿ, ನಾವು ಗಾಸ್ ಥಿಯರಮನ್ನು ಕ್ಲೋಸ್ಡ್ ಸರ್ಫೇಸ್ಗೆ ಮಾತ್ರ ಅಪ್ಲೈ ಮಾಡೋಕ್ಕೆ ಬರ್ತದೆ. ಅದಕ್ಕೆ ನೀವು ಪಾಯಿಂಟ್ ಪಿ ನಲ್ಲಿ ಇಂಟೆನ್ಸಿಟಿನ ಕಂಡುಹಿಡಿಬೇಕಂತಂದರೆ ನೀವು ಆ ಪಾಯಿಂಟ್ ಪಿ ಮೇಲೆ ಹಾದುವ ಒಂದು ಇಮ್ಯಾಜಿನರಿ ಸ್ಪಿಯರ್ನ ಕನ್ಸಿಡರ್ ಮಾಡ್ಕೋಬೇಕು. ಹೌದಾ? ಆ ಇಮ್ಯಾಜಿನ್ ಸ್ಪಿಯರ್ ಕನ್ಸಿಡರ್ ಮಾಡಿಕೊಂಡಾಗ ಆ ಇಮ್ಯಾಜಿನ್ ಸ್ಪಿಯರ್ದ ಯಾವುದೇ ಒಂದು ಪಾಯಿಂಟ್ ತಗೊಂಡ್ರೆ ಆ ಸರ್ಫೇಸ್ ಮೇಲೆ ಆ ಎಲ್ಲ ಪಾಯಿಂಟ್ಗಳು ಈಕ್ವಲ್ ಡಿಸ್ಟೆನ್ಸ್ ಅದಾವ ಸೆಂಟರ್ದಿಂದ. ಹೀಗಾಗಿ ಆ ಇಮ್ಯಾಜಿನರಿ ಸ್ಪಿಯರ್ದ ಎಲ್ಲ ಪಾಯಿಂಟ್ಗಳಲ್ಲಿ ಎಲೆಕ್ಟ್ರಿಕ್ ಇಂಟೆನ್ಸಿಟಿ, ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಸೇಮ್ ಇರ್ತದೆ ಮತ್ತು ಅದರ ಡೈರೆಕ್ಷನ್ನ ಆ ಸರ್ಫೇಸ್ಗೆ ಲಂಬವಾಗಿರ್ತದೆ, ನಾರ್ಮಲ್ ಆಗಿರ್ತದೆ. ಹಾಗಾದರೆ ಯಾವಾಗ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಲಂಬವಾಗಿದೆ ಮತ್ತು ಕಾನ್ಸ್ಟೆಂಟ್ ಇದೆಯೋ ಸರ್ಫೇಸ್ ಮೇಲೆ, ಅದಕ್ಕೆ ನಾವು ಗಾಸ್ ಥಿಯರಮನ್ನು ಅಪ್ಲೈ ಮಾಡ್ಬೋದು. ಯಾಕೆಂದ್ರೆ ಅಂಥ ಸರ್ಫೇಸ್ ನಾವು ಗೌಸಿಯನ್ ಸರ್ಫೇಸ್ ಅಂತ ಕರಿಬೋದು. ಹಂಗಾರೆ ಅಕಾರ್ಡಿಂಗ್ ಟು ಗಾಸ್ ಥಿಯರಮ್, we have the total electric flux across this Gaussian sphere is equal to 1 upon epsilon naught times of total charge enclosed by the surface. Here Q is the charge enclosed by this sphere. Getting the idea? Here flux means what? It is the total, here pi means this is the total flux across this Gaussian sphere. Here I will consider a small area. Here I have considered a small area delta S. We know that the area vector of this surface is acting in this direction. That is normal to the surface. Here area vector and electric field vector both are acting along same directions. Hence angle between E and delta S is 0 degree. Getting the idea? Now the total flux across this delta S only is given by E into delta S into cos theta. This is what? This is the flux through delta S only. But what is the total flux across whole Gaussian sphere? That is given by summation of E into delta S cos theta. That is equal to 1 upon epsilon naught into Q. Getting the idea? Illodi E into delta S cos theta ಅಂದ್ರೆ flux through delta S only. ಹಂಗಾರೆ ಈ ಟೋಟಲ್ ಫ್ಲಕ್ಸ್ ಅಕ್ರಾಸ್ ದ ಗೌಸಿಯನ್ ಸ್ಪಿಯರ್ ಅಂದರೆ ಸಮೇಷನ್ ಮಾಡಬೇಕು. ಅಂದ್ರೆ ಸಮೇಷನ್ ಆಫ್ ಇ ಇಂಟು ಡೆಲ್ಟಾ ಎಸ್ ಕಾಸ್ ಥೀಟಾ ಅಂತಂದ್ರೆ ಸಮೇಷನ್ ಮಾಡಿದರೆ ಎಲ್ಲ ಈ ಸ್ಪಿಯರ್ದಲ್ಲಿ ಇರ್ತಕ್ಕಂಥ ಎಲ್ಲ ಡೆಲ್ಟಾ ಎಸ್ಗಳಲ್ಲಿ ಎಷ್ಟು ಫ್ಲಕ್ಸ್ ಇದೆ ಎಂದು ಗೊತ್ತಾಗ್ತದೆ. ದಟ್ ಈಸ್ ಸಮೇಷನ್ ಆಫ್ ಇ ಇಂಟು ಡೆಲ್ಟಾ ಎಸ್ ಕಾಸ್ ಥೀಟಾ. ದಟ್ ಈಸ್ ಟೋಟಲ್ ಫ್ಲಕ್ಸ್ ಅಕ್ರಾಸ್ ದ ಗೌಸಿಯನ್ ಸ್ಪಿಯರ್. ದಿಸ್ ಮಚ್. Now electric intensity is same, constant at all points on this imaginary sphere. That's why it is taken outside. Summation of delta S into, here theta is 0 degree, cos 0 is 1. That is equal to 1 upon epsilon naught into Q. Getting the idea? Here you must remember, here E into summation of delta S means what? Area of Gaussian sphere. That is 4 pi r square. That is equal to 1 upon epsilon naught into Q. Therefore E is equal to 1 upon 4 pi epsilon naught into Q upon r square. Call it as equation 2. This is the electric intensity at a point P due to this charge sphere. Here we have calculated the intensity at a point P due to this charge sphere by using a Gauss theorem. And one more important point is, consider a point charge Q. Let P be a point at a distance r from the point charge Q. Then electric intensity at a point P, E is equal to 1 divided by 4 pi epsilon naught into Q upon r square. See here, this equation and this equation, this expression and this expression, both are same. What it indicates? Electric intensity at a point P due to charged sphere is this much. Electric intensity at a point P due to a point charge is also same. I think that both are same. This indicates what? If you charge the spherical conductor, it behaves like a point charge. That's why both are same. If you charge the spherical conductor, however, the charges are going to distribute over the outer surface of the spherical conductor, but those charges were concentrated at the center of the sphere. That's why sphere acts like a point charge. And these two expressions indicate that if you charge the spherical conductor, whatever the size of the spherical conductor, whether it is small or large, if you charge the spherical conductor, all the charges which are present over the outer surface of the conductor, those charges were concentrated at the center of the sphere. That's why a charge sphere acts like a point charge. Keep it in mind. This is very important thing. Now, already we have derived electric intensity at a point outside the sphere. Now, second condition, we are going to consider the consideration point inside the sphere. That is, point inside the sphere. Point inside the sphere. Point inside the sphere. Getting the idea? Point inside the sphere. So here I will consider a sphere of radius capital R. Let P be a point at a distance. How much? At a distance small letter r. At a distance small letter r is the center O. Here I have given a charge plus q coulomb. Q amount of charge is given. This charge distributes uniformly over the outer surface of the conductor. See here. Now the electric free lines are acting radially outward like this. Like this. Getting the idea? In this way, electric free lines are acting. Yes or no? These are the electric free lines which are acting radially outward. Why they are acting radially outward? Because the sphere is positively charged. Now, to find electric intensity at a point P, I will consider a closed surface of radius small r. See here. This is a closed surface of radius r. Then, if it is a closed surface, flux through this closed sphere phi is equal to 1 upon epsilon naught into total charge enclosed, called as equation 1. Here phi means what? Summation of E into delta S into cos theta is equal to Q upon epsilon naught. My dear students, you know that if I consider a small unit area delta S here, then area vector of this surface is also in this direction. That is delta S vector and area vector. Both are acting in the same direction and theta is equal to 0 degree. Here summation of E into delta S means what? The flux through this whole surface. E into delta S cos theta means flux through this delta S only. Summation of E into delta S cos theta means flux through this whole Gaussian sphere, whole sphere of radius r. That is, E is constant at all points, that's why it is taken outside, into summation of delta S cos 0 degrees 1, that is Q upon epsilon naught E into 4 pi summation of delta is 4 pi r square, that is equal to Q upon epsilon naught. E is equal to 1 divided by 4 pi epsilon naught into Q upon r square, called as equation 2. Since inside the sphere, no charge is enclosed. Inside the sphere, charge is 0. Therefore, equation 2 becomes what? Equation 2 becomes E is equal to 0, called as equation 3. In this way, inside the charge sphere there is no electric field. This is proved by using Gauss theorem. In this way, Gauss theorem can be used to determine electric intensity at a point due to a charge sphere. This question is going to be asked for 5 marks for your annual examination. So, as early as possible, make it perfect and understand all the concepts. Okay? My dear students, let us derive the expression for what is the electric intensity at a point due to a line charge, due to a charged wire by using Gauss theorem. This is also one of the applications of Gauss theorem. Now I will consider a wire here. I will consider a wire here. Consider a wire. This is a wire. Getting the idea? Now this wire is charged positively. Plus, 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 plus. Here, this is a charged wire, also called line charge. Since the wire is charged, it is having electric field around it. Okay. Now, I will consider a consideration point. Let P be a consideration point at a distance r, at a distance small letter r from the edges of the wire. Here point P is lying in the electric field of this charged wire. Now, how much intensity is produced at point P due to this charged wire? My dear students, once again you must keep in mind, here there is no single charge. Here many charges are going to distribute. That is, here also complex distribution of charge is there. That's why we are going to apply Gauss theorem here. My dear students, throughout the length, how much charge is present, how many charges are present, I don't know. Okay, that's why I consider whatever the charge is present in unit length, that is charge per unit length, is called what? Surface charge density. Okay, see here, per unit length, how many charges are there? That gives linear charge density. Sorry, it is not surface charge density, it is linear charge density. Now, lambda is the charge per unit length. Prati unit length alli lambda amount of charge ಇದೆ. That is, see here I will consider let lambda implies what? Linear charge density, that is charge per unit length. Charge per unit length of the wire, and R implies distance of consideration point. Distance of point P, distance of consideration point P. Getting the idea? And see here, if you want to calculate electric intensity at a point P by using Gauss theorem, okay, due to complex charge distribution over the length of the, along the length of the wire, you should apply Gauss theorem. If you want to apply Gauss theorem, you should consider a closed surface. So here I will consider a closed cylinder. Here I will consider a closed cylinder. See here. Here, this is also R, and here also I will consider consider a closed cylinder with two end caps. Why I have considered a cylinder here, a closed surface here? Because you are going to apply the Gauss theorem. By applying Gauss theorem, you are going to find the intensity at point P due to this charge wire. Okay. If you want to apply Gauss theorem, you should consider a closed cylinder such that the point P lies on the surface of the cylinder. Okay, and let L be the length of this imaginary Gaussian cylinder. Length of this imaginary cylinder. Getting the idea? That is, L means what? Length of Gaussian cylinder. Length of Gaussian cylinder. Getting the idea? ನಾನು ಯಾಕೆ ಈ ಕ್ಲೋಸ್ ಸರ್ಫೇಸನ್ನು ಕನ್ಸಿಡರ್ ಮಾಡ್ಕೊಂಡು ಅನ್ನೋದು ನಿಮಗೆ ಗೊತ್ತಿರಬೇಕು. ಯಾಕಂದರೆ ಕ್ಲೋಸ್ ಸರ್ಫೇಸ್ಗೆ ಮಾತ್ರ ನಮಗೆ ಗಾಸ್ ಲಾನ ಅಪ್ಲೈ ಮಾಡ್ಬೋದು. ಅದಕ್ಕೆ ನೀವು ಪಾಯಿಂಟ್ ಪಿ ನಲ್ಲಿ ಇಂಟೆನ್ಸಿಟಿ ಕಂಡಿಬೇಕಪ್ಪ ಅಂತಂದ್ರೆ ಆ ಪಾಯಿಂಟ್ ಪಿ ಆ ಸಿಲಿಂಡರ್ ಮೇಲೆ ಬಂದಿರಬೇಕು. ಆ ರೀತಿ ಒಂದು ಸಿಲಿಂಡರ್ನ ಕ್ಲೋಸ್ ಸರ್ಫೇಸನ್ನು ನೀವು ಕನ್ಸಿಡರ್ ಮಾಡ್ಕೋಬೇಕು. ಇಲ್ಲಿ ನೋಡಿ, ವಾಟ್ ಇಸ್ ದ ಲೆಂತ್ ಆಫ್ ದಿಸ್ ಸಿಲಿಂಡರ್? ಎಲ್. ಲೆಟ್ area of cross section of this cylinder is capital A ಅನ್ನೋಣ. ಓಕೆ, getting the idea? ಇಲ್ಲಿ ಎರಡು ಎಂಡ್ ಕ್ಯಾಪ್ಸ್ ಅದಾವ ಮತ್ತು ಇದು ಕರ್ವ್ಡ್ ಸರ್ಫೇಸ್ ಐತಿ. getting the idea? Now flux across the curved part of the cylinder. Therefore electric flux across the curved part of Gaussian cylinder is electric flux across the curved part of the Gaussian cylinder. ನೋಡಿ, ಇದು ಕರ್ವ್ಡ್ ಪಾರ್ಟ್. ಇವು ಎರಡು ಎಂಡ್ ಕ್ಯಾಪ್ಸ್, ಅಪ್ಪರ್ ಲೋವರ್. ಈ ಕರ್ವ್ಡ್ ಪಾರ್ಟ್ದಲ್ಲಿ ಎಷ್ಟು ಫ್ಲಕ್ಸ್ ಇದೆ? ಹಿಯರ್ ಇಫ್ ಐ ಕನ್ಸಿಡರ್ ದಿಸ್ ಏರಿಯಾ, ಓಕೆ, ಇಲ್ಲಿ ನೋಡಿ, ಸಿನ್ಸ್ ಇಟ್ ಇಸ್ ಪಾಸಿಟಿವ್ಲಿ ಚಾರ್ಜ್, ಎಲೆಕ್ಟ್ರಿಕ್ ಇಂಟೆನ್ಸಿಟಿ ಅಟ್ ಪಾಯಿಂಟ್ ಪಿ ಆಕ್ಟ್ಸ್ ರೇಡಿಯಲಿ ಔಟ್ವರ್ಡ್ ಡೈರೆಕ್ಷನ್ ಲೈಕ್ ದಿಸ್. ಗೆಟಿಂಗ್ ದಿ ಐಡಿಯಾ? ಯಾಕಿದು ರೇಡಿಯಲಿ ಔಟ್ವರ್ಡ್ ಐತಿ? ಇದು ಪಾಸಿಟಿವ್ಲಿ ಚಾರ್ಜ್ ಐತಿ. ಅದಕ್ಕೆ ಅಂದ್ರೆ ಇಫ್ ಇಟ್ ಈಸ್ ಡೆಲ್ಟಾ ಎಸ್, it is the small amount of area. The area vector of this surface is also in this direction. ಅಂದರೆ ಇಲ್ಲಿ ಕೂಡ ಏರಿಯಾ ವೆಕ್ಟರ್, ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ವೆಕ್ಟರ್, both are acting along same direction and theta is equal to 0 degree. ಇಲ್ಲಿ ನೋಡಿ, ನಾನು ಸ್ಮಾಲ್ ಏರಿಯಾನ ಕನ್ಸಿಡರ್ ಮಾಡ್ಕೊಂಡೀನಿ ಆ ಕರ್ವ್ಡ್ ಪಾರ್ಟ್ದಲ್ಲಿ. ಈ ಕರ್ವ್ಡ್ ಸರ್ಫೇಸ್ದಲ್ಲಿ ಒಂದು ಸ್ಮಾಲ್ ಏರಿಯಾ ಕನ್ಸಿಡರ್ ಮಾಡ್ಕೊಂಡೀನಿ, ಅದು ಡೆಲ್ಟಾ ಎಸ್. ಅದರ ಏರಿಯಾ ವೆಕ್ಟರ್ ಆ ಸರ್ಫೇಸ್ಗೆ ಲಂಬ ಇದೆ. The electric field area vector, both are acting along same direction, hence theta becomes 0 degree. Now, what is the flux across this delta S? That is flux across delta S. That is equal to E into delta S into cos theta. ಹಿಂಗಂದ್ರೆ this is the flux through delta S only. ನಮಗೇನು ಬೇಕು? ಫ್ಲಕ್ಸ್ ಅಕ್ರಾಸ್ ದ ಹೋಲ್ ಕರ್ವ್ಡ್ ಪಾರ್ಟ್ ಆಫ್ ದ ಸಿಲಿಂಡರ್ ಬೇಕಾಯ್ತು. ಅಂದ್ರೆ ಈ ಸಿಲಿಂಡರ್ದಲ್ಲಿ ಬರ್ತಕ್ಕಂಥ ಎಲ್ಲಾ ಡೆಲ್ಟಾ ಎಸ್ಗಳಲ್ಲಿ ಎಷ್ಟು ಫ್ಲಕ್ಸ್ ಐತಿ ಒಟ್ಟಾರೆಯಾಗಿ? ದಟ್ ಈಸ್ ಸಮೇಷನ್ ಆಫ್ ಇದಕ್ಕೆ φ1 ಅಂತ. ಅಂದ್ರೆ φ1 ಅಂದ್ರೇನು? ಇಟ್ ಈಸ್ ದ ಟೋಟಲ್ ಫ್ಲಕ್ಸ್ ಅಕ್ರಾಸ್ ದ ಕರ್ವ್ಡ್ ಪಾರ್ಟ್ ಆಫ್ ದ ಗೌಸಿಯನ್ ಸಿಲಿಂಡರ್. ದಟ್ ಈಸ್ φ1 is equal to summation of E into delta S cos theta. ಅಂದ್ರೆ ಎಷ್ಟಾಗ್ತದೆ ಇದು? φ1 is equal to E is constant. ನೋಡಿ, ಇಲ್ಲಿ ಎಲೆಕ್ಟ್ರಿಕ್ ಎಷ್ಟೈತಿ? ಇಲ್ಲಿ ಅಷ್ಟ ಇದೆ. ಓಕೆ, ಇಲ್ಲಿ ಈನ ಐತಿ, ಇಲ್ಲಿ ಕೂಡ ಈನ ಇದೆ, ಹೌದಾ? ಆಮೇಲೆ ಇಲ್ಲಿ ಕೂಡ ಈನ ಇದೆ ಎಲೆಕ್ಟ್ರಿಕ್ ಇಂಟೆನ್ಸಿಟಿ, ಇಲ್ಲಿ ಕೂಡ ಈನ ಐತಿ, ಹೌದಾ? ಎಲ್ಲ ಕಡೆ ಇಂಟೆನ್ಸಿಟಿ ಸೇಮ್ ಇದೆ, ಹೌದಾ? ಹಂಗಾರೆ ಇಟ್ ಇಸ್ ಟೇಕನ್ ಔಟ್ ಸೈಡ್. ದೆನ್ ಸಮೇಷನ್ ಆಫ್ ಡೆಲ್ಟಾ S cos 0 is 1. Getting the idea? Therefore φ1 is equal to E into summation of delta S, area of cylinder. area of cylinder 2 pi r L. Call it as equation 1. This is the flux through curved part of the Gaussian cylinder. What is the flux through the two end caps? Okay, therefore flux through two end caps, electric flux across the two end caps of Gaussian cylinder is flux through the upper end cap. Phi2 is equal to flux through lower end cap, that is Phi3. ಇದ್ರ ಮುಖಾಂತರ ಫ್ಲಕ್ಸ್ ಎಷ್ಟಿದೆ, ಈ ಎಂಡ್ ಕ್ಯಾಪ್ ಮುಖಾಂತರ ಎಷ್ಟು ಫ್ಲಕ್ಸ್ ಇದೆ, ಈ ಎಂಡ್ ಕ್ಯಾಪ್ ಮುಖಾಂತರ ಎಷ್ಟು ಫ್ಲಕ್ಸ್ ಇದೆ. ಫ್ಲಕ್ಸ್ ಥ್ರೂ ಅಪ್ಪರ್ ಎಂಡ್ ಕ್ಯಾಪ್ ಈಸ್ Phi2, ಫ್ಲಕ್ಸ್ ಥ್ರೂ ಲೋವರ್ ಎಂಡ್ ಕ್ಯಾಪ್ ಈಸ್ Phi3. ಎರಡು ಈಕ್ವಲ್ ಇದಾವೆ, ಯಾಕಂದ್ರೆ ಏರಿಯಾ ಆಫ್ ಕ್ರಾಸ್ ಸೆಕ್ಷನ್ ಸೇಮ್ ಐತಿ. ಹೌದಾ? ಹಾಗಾದ್ರೆ ಇಲ್ಲಿ ನೋಡಿ, ಈ ಕ್ರಾಸ್ ಸೆಕ್ಷನ್ ಇದ್ದು ಏರಿಯಾ ವೆಕ್ಟರ್ ಇಟ್ ಈಸ್ ಆಲ್ವೇಸ್ normal to this surface. E cross section area vector it is also normal to the surface, that is here delta s vector, here also delta x vector. Nodri, e upper end cap of the area vector normal to the surface, e lower end cap of the area vector normal to the surface. ಅಂದ್ರೆ ಇಲ್ಲಿ ಥೀಟಾ ಏನಾಯಿತು, ಆ್ಯಂಗಲ್ ಬಿಟ್ವೀನ್ ಡೆಲ್ಟಾ ಎಸ್ ವೆಕ್ಟರ್ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ವೆಕ್ಟರ್ ಏನಾಯಿತು, 90 ಡಿಗ್ರಿ ಆಯಿತು. ಇಲ್ಲಿ ಕೂಡ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ವೆಕ್ಟರ್ ಈ ಕಡೆ ಇದೆ, ಏರಿಯಾ ವೆಕ್ಟರ್ ಈ ಕಡೆ ಇದೆ, and this is also theta is equal to 90 degree. ಹಂಗಾರೆ see here summation of E into delta S into cos 90 degree, that is equal to 0, called it as equation 2. Andra flux through two end caps is always 0. Why it is 0? Because angle between area vector and electric field vector is 90 degree. That's why flux through upper end cap, lower end cap is 0. Therefore total flux across the Gaussian cylinder, therefore total flux across Gaussian cylinder is phi is equal to phi1 plus phi2 plus phi3, call it as equation 3. Therefore total flux is equal to phi1 is E into 2 pi r L plus 0, call it as equation 4. This is the total flux across the Gaussian cylinder. Also we have from Gauss theorem, we have total flux across any closed surface is equal to 1 upon epsilon naught into total charge enclosed, called as equation 5. Therefore flux is this much. Flux of the Gaussian cylinder is E into 2 pi r L, that is equal to Q is lambda into L divided by epsilon naught. This is because linear charge density lambda is equal to Q upon L, amount of charge per unit length of the wire, that is Q is equal to lambda into L. Therefore E is equal to L cancel, then lambda divided by 2 pi epsilon naught into R, equation 6. This is the expression for electric intensity at point P due to the charged wire. Here lambda is amount of charge per unit length of the wire. Getting the idea? R is the perpendicular distance of the point P from the axis of the wire. Getting the idea? This is the expression for electric intensity at point P due to a charged wire. Here we have find the electric intensity at point P due to a charged wire by using Gauss theorem. This is also one of the applications of Gauss theorem. This is also for 5 marks. Keep in mind. Okay friends, now one more derivation I am going to derive, that is electric intensity at a point due to a charged plane sheet by using Gauss theorem. Now let us consider a plane sheet here. This is a plane sheet. Getting the idea? Now this plane sheet is having positive charge on its surface. In this way, electric field is present at front side and at back side. Now I will consider a point P here at the front side. Now I will consider a point P at the front side at a distance small letter r from the surface of the plane sheet. Here, this is the point P. Getting the idea? Here also, many charges are going to distribute on the outer surface of the plane sheet. That's why we have to use Gauss theorem. If you want to use Gauss theorem, you should consider a closed surface. Here also I am going to consider a closed surface, such that here I am going to consider a cylinder. Here I am going to consider a cylinder here. There is a cylinder of length 2r. What is the length of this Gaussian cylinder? 2r. That is, half of the cylinder is present at front and another half is present at the back side. That's why we should apply symmetry. That's why I have considered like this. Okay. Here, what I have considered? Here I have considered a cylinder of length 2r. Half of the cylinder is present at front side and the other half is present at the back side. Okay. Now symmetry is going to be applied. See here, this is our Gaussian cylinder. This is our closed surface. Why I have considered this closed surface? In order to find electric intensity at a point P by using Gauss theorem. Okay. Now, per unit area, I will consider some amount of charge. Let Q be the amount of charge. Let Q be the amount of charge per unit area of the surface. That is called what? Surface charge density. ಪ್ರತಿ ಯೂನಿಟ್ ಏರಿಯಾದಲ್ಲಿ ಎಷ್ಟು ಅಮೌಂಟ್ ಆಫ್ ಚಾರ್ಜ್ ಇದೆ? ಕ್ಯೂ ಇದೆ. ಅದನ್ನು ನಾವು ಸಿಗ್ಮಾ ಅಂತ ಸೂಚಿಸ್ತೇವೆ. ಸಿಗ್ಮಾ ಅಮೌಂಟ್ ಆಫ್ ಚಾರ್ಜ್ ಪ್ರತಿ ಯೂನಿಟ್ ಏರಿಯಾ ಆಫ್ ದಿಸ್ ಸರ್ಫೇಸ್ ನಲ್ಲಿ ಇದೆ. ಹೌದಾ? ಹಾಗಾದ್ರೆ ಇಲ್ಲಿ ನೋಡಿ, ಹಿಯರ್ ದ plane sheet is charged positively. Electric intensity at a point P is acting in this direction. Why it is acting in outward direction? Because it is positively charged. ಇದು ಪಾಸಿಟಿವ್ ಆಗಿ ಚಾರ್ಜ್ ಇರೋದ್ರಿಂದ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಲೈನ್ಸ್ ಲಂಬವಾಗಿ ಆಗ್ತಾ ಇರ್ತವೆ ಚಾರ್ಜ್ ಸರ್ಫೇಸ್ಗೆ. ಪ್ರಾಪರ್ಟೀಸ್ ಆಫ್ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಲೈನ್ಸ್ ಅಲ್ಲಿ ಓದಿರಿ. ಯಾವುದೇ ಒಂದು ಚಾರ್ಜ್ ಸರ್ಫೇಸ್ ಇತ್ತಂದ್ರೆ ಅದಕ್ಕೆ ಲಂಬವಾಗಿ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಲೈನ್ಸ್ ಆಕ್ಟ್ ಆಗ್ತಿರ್ತಾವೆ. ಹಂಗಾರೆ ಸಿನ್ಸ್ ಇಟ್ ಇಸ್ ಪಾಸಿಟಿವ್ಲಿ ಚಾರ್ಜ್, ಎಲೆಕ್ಟ್ರಿಕ್ ಇಂಟೆನ್ಸಿಟಿ ಅಟ್ ಪಾಯಿಂಟ್ ಪಿ ಆಕ್ಟ್ಸ್ ಇನ್ ದಿಸ್ ಡೈರೆಕ್ಷನ್. ಇದು ನೆಗೆಟಿವ್ ಚಾರ್ಜ್ ಆಗಿರ್ತಾರೆ, ಎಲೆಕ್ಟ್ರಿಕ್ ಇಂಟೆನ್ಸಿಟಿ ಈ ಕಡೆ ಇರ್ತಿತ್ತು. ಓಕೆ, ನೌ ಹಿಯರ್ I will write the area vector delta S. Okay, delta S ಅಂದ್ರೆ it is the area surrounding the point P only. ಇಲ್ಲಿ delta S ಅಂದ್ರೆ It is an area surrounding the point P, and the area vector of this area of this point P is also acting in this direction. Under delta S vector, electric field vector, both are acting same direction, hence theta is equal to 0 degree. Illodi delta S andreno, it is the area surrounding the point P only. ಅಂದ್ರೆ ಆ ಪಾಯಿಂಟ್ ಪಿ ದಲ್ಲಿ ಇರ್ತಕ್ಕಂಥ ಏರಿಯಾ ಎಷ್ಟು ಡೆಲ್ಟಾ ಎಸ್, ಅದು ಯಾವ ಕಡೆ ಇದೆ ಅದರ ವೆಕ್ಟರ್ ಈ ಕಡೆ ಇದೆ, ಅಂದ್ರೆ ಇದಕ್ಕೆ ಲಂಬವಾಗಿ. Here delta S is the area surrounding the point P and its area vector is in this direction. Electric field is in this direction. That's why theta is 0 degree. ಹಾಗಾದ್ರೆ ಇಲ್ಲಿ ನೋಡಿ ನಾವು, what is the flux across the curved part of the Gaussian cylinder and what is the flux across the two end caps of the Gaussian cylinder. ಅದೇ ರೀತಿ ಇಲ್ಲಿ ಕೂಡ, ಇಲ್ಲಿ ಪಾಯಿಂಟ್ ಪಿ ಇರೋದಾದ್ರೆ ಇಲ್ಲಿ ಪಾಸಿಟಿವ್ ಚಾರ್ಜ್ ಇದೆ, ಎಲೆಕ್ಟ್ರಿಕ್ ಇಂಟೆನ್ಸಿಟಿ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಈ ಕಡೆ ಆಕ್ಟ್ ಆಗ್ತದ. ಹಾಗಾದ್ರೆ ಇಲ್ಲಿ ಕೂಡ ಏರಿಯಾ ವೆಕ್ಟರ್ ಏನಾಗಿದೆ, ಆಕ್ಟಿಂಗ್ ಇನ್ ದಿಸ್ ಡೈರೆಕ್ಷನ್. ಇಲ್ಲಿ ಥೀಟಾ ಇಸ್ ಈಕ್ವಲ್ ಟು 0 ಡಿಗ್ರಿ ಆಗಿದೆ. ಹಾಗಾದ್ರೆ ಫ್ಲಕ್ಸ್ ಥ್ರೂ ದ ಟು ಎಂಡ್ ಕ್ಯಾಪ್ಸ್ ಇಸ್ ವಾಟ್ ಅಂಡ್ ಫ್ಲಕ್ಸ್ ಥ್ರೂ ದ ಕರ್ಡ್ ಪಾರ್ಟ್ ಆಫ್ ದ ಸಿಲಿಂಡರ್ ಇಸ್ ವಾಟ್. ಇಲ್ಲಿ ನೋಡ್ರಿ, ಎರಡು ಎಂಡ್ ಕ್ಯಾಪ್ಗಳಿಗೆ ಥೀಟಾ 0 ಡಿಗ್ರಿ ಆಗಿದೆ. ಎರಡು ಎಂಡ್ ಕ್ಯಾಪ್ಗಳಿಗೆ ಆಂಗಲ್ ಬಿಟ್ವೀನ್ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ವೆಕ್ಟರ್ ಆ್ಯಂಡ್ ಏರಿಯಾ ವೆಕ್ಟರ್ ಥೀಟಾ ಇಸ್ 0 ಡಿಗ್ರಿ. ಆದರೆ ವಾಟ್ ಈಸ್ ದ ಎಲೆಕ್ಟ್ರಿಕ್ ಫ್ಲಕ್ಸ್ ಅಕ್ರಾಸ್ ದ ಕರ್ಡ್ ಸರ್ಫೇಸ್ ಅನ್ನೋದನ್ನು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಬೇಕಂದ್ರೆ ಇಲ್ಲಿ ನೋಡ್ರಿ, ಈ ಕರ್ಡ್ ಸರ್ಫೇಸ್ ಏರಿಯಾ ವೆಕ್ಟರ್ ನೋಡ್ರಿ, ಇದು ಕರ್ಡ್ ಸರ್ಫೇಸ್, ಇದ್ರ ಏರಿಯಾ ವೆಕ್ಟರ್ ಯಾವ ಕಡೆ ಐತಿ, ಈ ಕಡೆ ಐತಿ. ಎಸ್ ಆರ್ ಇಫ್ ಇಟ್ ಈಸ್ ಡೆಲ್ಟಾ ಎಸ್, ಇದ್ರ ಏರಿಯಾ ವೆಕ್ಟರ್ ಯಾವ ಕಡೆ, ಈ ಕಡೆ, ದಟ್ ಈಸ್ ಡೆಲ್ಟಾ ಎಸ್ ವೆಕ್ಟರ್. ಆದರೆ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ವೆಕ್ಟರ್ ಈ ಕಡೆ ಐತಿ, ದಟ್ ಈಸ್ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ವೆಕ್ಟರ್. ನೋಡ್ರಿ ಇಲ್ಲಿ ಏನಾಯ್ತು, ಥೀಟಾ ಥೀಟಾ ಈಸ್ 90 ಡಿಗ್ರಿ. ಅಂದರೆ ಫಾರ್ ಕರ್ಡ್ ಪಾರ್ಟ್ ಆಫ್ ದ ಗೌಸಿಯನ್ ಸಿಲಿಂಡರ್ ಥೀಟಾ ಇಸ್ 90 ಡಿಗ್ರಿ. ಯಾಕಂತಾರೆ ಈ ಕರ್ಡ್ ಪಾರ್ಟ್ ದ ಏರಿಯಾ ವೆಕ್ಟರ್, ಇಲ್ಲಿ ಡೆಲ್ಟಾ ಎಸ್ ಇದೆ, ಈ ಡೆಲ್ಟಾ ಎಸ್ ಏರಿಯಾ ವೆಕ್ಟರ್ ಯಾವಾಗಲೂ ನಾರ್ಮಲ್ ಇರ್ತದೆ. ಆದರೆ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಈ ಕಡೆ ಐತಿ, ಅಂದರೆ ಥೀಟಾ 90 ಡಿಗ್ರಿ. ಇಲ್ಲಿ ಕೂಡ ನೋಡ್ರಿ, ಇದ್ರ ಏರಿಯಾ ವೆಕ್ಟರ್ ಈ ಕಡೆ ಡೆಲ್ಟಾ ಎಸ್, ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ವೆಕ್ಟರ್ ಈ ಕಡೆ ವೆಕ್ಟರ್ ಇ, ಮತ್ತು ಥೀಟಾ ಏನಾಯ್ತು, ದಟ್ ಈಸ್ ಅಗೇನ್ 90 ಡಿಗ್ರಿ. ಗೆಟಿಂಗ್ ದಿ ಐಡಿಯಾ. ಹಂಗಾರೆ ಎಲೆಕ್ಟ್ರಿಕ್ ಫ್ಲಕ್ಸ್ ಈಗ ನೋಡಿ, ಫಸ್ಟ್ ನಂಬರ್ ಕೊಡ್ತೀನಿ. ಸಿಗ್ಮಾ ಅಂದ್ರೇನು, ಸರ್ಫೇಸ್ ಚಾರ್ಜ್ ಡೆನ್ಸಿಟಿ, ಅಂದರೆ ಚಾರ್ಜ್ ಪರ್ ಯೂನಿಟ್ ಏರಿಯಾ, ಚಾರ್ಜ್ ಪರ್ ಯೂನಿಟ್ ಏರಿಯಾ, ಚಾರ್ಜ್ ಪರ್ ಯೂನಿಟ್ ಏರಿಯಾ. ಓಕೆ, ನೆಕ್ಸ್ಟ್ ಆರ್ ಅಂತಂದರೆ ಡಿಸ್ಟೆನ್ಸ್ ಆಫ್ ಕನ್ಸಿಡರೇಷನ್ ಪಾಯಿಂಟ್, ಡಿಸ್ಟೆನ್ಸ್ ಆಫ್ ಕನ್ಸಿಡರೇಷನ್ ಪಾಯಿಂಟ್ ಪಿ. ಹೌದಾ, ನೆಕ್ಸ್ಟ್ ಓಕೆ ಓಕೆ ನಾವು flux across the curved part of the Gaussian cylinder. Therefore, electric flux across the curved part of Gaussian cylinder is what? Is phi 1 is equal to summation of E into delta S. Notice E into delta S into cos 90 degree, that is equal to 0. Call it as equation 1. ಇಲ್ಲೊಂದು ತಗೋಬೇಕು, ಈ ಸಮೇಷನ್ ತೆಗೆದು E into delta S cos 90 ಅಂದರೆ ಇದು ದ ಫ್ಲಕ್ಸ್ ಥ್ರೂ ಡೆಲ್ಟಾ ಎಸ್ ಓನ್ಲಿ. ಇಲ್ಲಿ ಸಮೇಷನ್ ಹಾಕಿದೆ ಅಂತಂದ್ರೆ ಈ ಕರ್ಡ್ ಸರ್ಫೇಸಲ್ಲಿ ಇರ್ತಕ್ಕಂಥ ಎಲ್ಲ ಡೆಲ್ಟಾ ಎಸ್ಗಳಲ್ಲಿ ಒಟ್ಟಾರೆಯಾಗಿ ಎಷ್ಟು ಫ್ಲಕ್ಸ್ ಇದೆ ಅಂತ ಗೊತ್ತಾಗ್ತದೆ, ಅದು ಕೂಡ 0 ಆಗಿರ್ತದೆ. ಯಾಕಂದರೆ ಆ್ಯಂಗಲ್ ಬಿಟ್ವೀನ್ ಇ ಆ್ಯಂಡ್ ಡೆಲ್ಟಾ ಎಸ್ ಇಸ್ 90 ಡಿಗ್ರಿ. ಹೌದಾ, ನಾವು ಫ್ಲಕ್ಸ್ across the two end caps is what? Flux through two end caps is what? Phi 2 is equal to phi 3 is equal to summation of E into delta S into cos theta. Getting the idea? Now E is constant. E is constant at all points. That's why it's taken outside. Summation of delta S cos 0 is 1. That is equal to E into delta S ಅಂದ್ರೆ ಏರಿಯಾ ಸರೌಂಡಿಂಗ್ ದ ಪಾಯಿಂಟ್ ಪಿ. ಹಂಗಾರೆ ಈ ಕ್ರಾಸ್ ಸೆಕ್ಷನಲ್ಲಿ ಇರ್ತಕ್ಕಂಥ ಎಲ್ಲ ಡೆಲ್ಟಾ ಎಸ್ಗಳನ್ನು ಒಟ್ಟಾರೆಯಾಗಿ ಕ್ಯಾಪಿಟಲ್ ಎ ಅಂತ ಕರೆದು ಅಂದ್ರೆ ಕ್ಯಾಪಿಟಲ್ ಎ ಇಂಪ್ಲೈಸ್ ವಾಟ್ ಗೊತ್ತಂದ್ರೆ ಕ್ಯಾಪಿಟಲ್ ಎ ಇಂಪ್ಲೈಸ್ ವಾಟ್ ಏರಿಯಾ ಆಫ್ ಕ್ರಾಸ್ ಸೆಕ್ಷನ್. ಏರಿಯಾ ಆಫ್ cross section of the two end caps. Okay, the summation of delta is the area of cross section of this end cap, that is capital A. Okay, call it as equation 2. Therefore total flux across the Gaussian cylinder, therefore total flux across Gaussian cylinder is phi is equal to phi 1 plus phi 2 plus phi 3, called it as equation 3. Therefore phi is equal to phi 1 is 0, phi 2 is E into A, phi 3 is also E into A. Therefore total flux is equal to 2E into A, called it as equation 4. From Gauss theorem we have total flux across this Gaussian cylinder is equal to Q upon epsilon naught, called it as equation 5. Here flux across this Gaussian cylinder is 2EA. Q is what? Surface charge in sigma is equal to Q upon A. Therefore Q is equal to sigma into A divided by epsilon naught. Getting the idea? A cancel. Therefore E is equal to sigma divided by 2 upon sigma divided by 2 epsilon naught. This is the electric intensity at a point P due to the charged plane sheet having surface charge density sigma. This is also for 5 marks. Please make it perfect.